So I forgot about the third video back in December whenever I did the first and second video on alternate series tests. So here's our third video now. Now here's the problem in terms of Unit 2. Okay. We have only learned how to find an exact sum by using geometric series and telescoping series and nothing else. Those are the only two that we have know how to find a sum for. Unfortunately, that's it for this course. Now, at this point, we're just going to do a game of guesstimating. And that's where the first guesstimating comes into play, which is called the alternating series error or alternating series remainder. Basically, you're going to confirm that the series is an alternating series, and then we are going to find the error in terms of approximating it in terms of the actual sum. So, if r sub n is the actual sum, which what is r sub n? Oh, r sub n is the remainder. So r sub n is going to be the remainder, and s is going to be the actual sum. Now, like I said, we don't know what the actual sum is. So what we're going to do is approximate it using the nth partial sum. So the remainder here is going to be the actual sum, which we don't know, minus the nth partial sum. Now, you might be thinking, okay, but how do we find the remainder, given that we don't know what the actual sum is? Well, this is where we have to use the alternating series remainder. Basically, r sub n is going to be less than or equal to the next neglected term in our series. So in this case, notice how we have the nth partial sum. So we're just going to take the next neglected term, and that's going to be our maximum error. And then that's going to help us in terms of finding out an approximation of our sum in terms of our series. All right, that was a lot, I know. So probably go back and rewind the video if you didn't understand what I said, or probably just look at the examples that I'm about to give you. So for number 15 here, we are going to find this sum right here using a calculator. I guess I have to pull up my handy dandy calculator, huh? All right, so let's see. Hopefully we don't get any ads. Summation is going to be at the very bottom. We have 1 all the way to 10. We have -1 to the n. And then we have 1 over x to the x. And that gives us -0.7834305,107. Actually, just kidding. That's n plus 1. So it should just the positive answer. 0.78343. Now I'm going to use as many decimal places as I can so that you can see what's going to happen here. So we have this sum right here. And that is the partial sum for the first 10 terms. Now the problem is I don't want to find the partial sum for the first 10 terms. I actually want to find the sum of the series, of the infinite series, which is going to be part B. Actually, no. We'll actually leave that for number 16. For part B, it's going to talk about what's the maximum value of this error. Now, because we're using, let's see, the first 10 terms, the maximum error is going to be the next neglected term, which is going to be term number 11. So that is actually going to be -1 to the, what is that? The 11th term, so that's going to be 12. And then 1 over 11 to the 11. Now, notice how my maximum error is an absolute value, so you want to do that. So this right here is going to be my maximum error. Now, if we use the first 20 terms instead of 10, would the error increase or decrease? well, the more terms that we have, the more accurate the series is going to get in terms of our sum. So the more terms we have, the more terms, the less of an error. All right, so we are going to see what that means in terms of number 16, where we actually find out the bound. So for number 16, it tells us to find what the actual sum is using the first 6 terms. Now, I already gave you that the actual sum is 0.632121. So what we're going to do here is look at the first 6 terms. Now, because we're using the first 6 terms, we are going to use the 7th term in terms of our neglected term. Now, what I forgot to mention on number 15, which I should have done, was actually verify that the alternating series test actually worked for this one. So for number 15 and 16 and 17 and 18, you probably want to write down the little statements that I gave you in the first video and the second video, where I tell you alternating series error may be used because the terms in the series decrease in absolute value to 0. I know. Okay. So we're going to use the next neglected term. So whenever we have our alternating series error right here, we have our actual sum that we don't know. We have the 6 partial sum that we're going to find out. And then we have our neglected term, which is going to be a sub 7. Now, what we have to do here is actually plug and chug to find out the 6 partial sum, and then figure out what a sub 7 is. So, let's see, x, 1, 6, and then we have -1 to the 7th. Actually, no. It's n minus 1. Oh, plus 1. Then 1 over n factorial. Close that. And that gives us our sum of 0.6319444444. So we have 0.63194. And then we are going to look at the next neglected term, aka a sub 7 here. Oops, not Desmos, a sub 7. So we are going to, I'm actually going to actually find the value of it, because we want to find what s could be. Oh, Jesus. Oh, wait, that's e to the -4. So if that's e to the -4, 1.9841. One, two, three, 4. So my next neglected term is 00019, essentially. All right, so then we're just going to solve this like a regular schmegler inequality that we did back in Math 3, where we just add and subtract from my partial sum here, meaning that my actual sum is between 0.63175 and 63213. Now, I already told you what the actual sum is, which was 0.632121, which of course fits in with our inequality here. Let's see. Like I said earlier, the more terms we have, the more accurate our sum is going to be, which means that's the less of an error that we're going to have. So we're going to look at number 18 closely whenever we do 17 in terms of the smallest value for which the partial sum approximates within 0.005. All right, so looking at number 17 here, we want to find the upper bound of the sum if the first four terms are used for S sub n. Now, if the first four terms are used, we're going to use the next neglected term. So that is going to be a sub 5. Now, do you have to write this? No. You could just write error and we'll be okay with that. And then a sub 5 is going to be negative 1 to the 5th, 5 factorial, which is 1 over 5 factorial. Of course, make sure that on the FRQ, if you're given an FRQ, that you verify that this is an alternate series error. Terms decrease in the series to absolute value to 0. But that would be your work in terms of finding my error, my upper bound for error, my maximum error. So whenever I say something like upper bound, that just basically means find my maximum error. All right, so for number 17 here, we want to find the smallest value for n of n for which S sub n, so the n partial sum, approximate the sum within 0.005. So the problem is that whenever we're doing the error, we don't know what our next neglected term is going to be. But we do know that it has to be within 0.005. All right, so our next neglected term, if I were to think about this right here, we are just going to put everything in terms of n plus 1 now. So this is going to be my next term. What's my next term? I don't know, but that's my next term. And it needs to be within 0.005. Now that's negative 1 to the n plus 1. I honestly do not really care about it because we are using absolute value. So I'm actually going to take that out. And then what I'm also going to do here is, because this is theoretically calculator inactive, I'm going to rewrite 0.005 as 5 over 1,000. Now I'm going to do some magic here in terms of that. And then I'm going to think about, okay, what is going to give me something larger than 200 in terms of my factorial? In this case, we know that 5 factorial is 120, and 6 factorial, 5 factorial is 120, right? Yeah, 120, which means that 6 factorial is 720. So that means that n has to be 5 in order for this to be 6. Of course, you kind of have to remember your factorials, but I think that's like easy peasy lemon squeezy. So this means that if n is equal to 5, that means that my partial sum for the first 5 terms is going to approximate the sum within 0.005. The actual sum within 0.005. So here's what I'm going to do. Because we're using the next neglected term, the next neglected term is actually going to be term number 6, which means that I'm going to look at this right here and evaluate this in terms of a sub 6. And we're going to see that that's going to be within 0.005. I'll just use osmose. So 1, 0, oop. Well, actually, I'll do term number 5 first. So if 5 was my next neglected term, If 5 was my next neglected term, which was actually number 17, you will see that that is within 0.008 and not within 0.005. Whereas if I do 1 over 6 factorial, my error is within 0.005, or more precisely, it is within 0.001, which is what we want. Which means in order to get to 1 over 6 factorial, we need the first 5 terms to approximate the sum within 0.005, or more precisely 0.001. All right. Oh, okay. Two more problems. For number 19 here, it tells us to find the 6 partial sum and then use that to show that this value is less than 3 over 1,000. Now, a lot of problems on the FRQ is going to be like number 19 here, where it's going to tell you, show that this happens. Now, in order for you to do that, you probably want to, once again, verify that the conditions work, aka alternate series error will be used because terms in the series decrease in absolute value to 0. We're going to find out what the 6 partial sum is. I'm going to go with Desmos because I'm too lazy to use Miss TI-84. Let's see, 1, the 6 partial sum, -1 to the, oops, n minus 1 times 3 all over 2 to the n plus 1. Okay, so my 6 partial sum is 0.565. Now, like I said earlier on number 17, you do not have to write this, right? So you could write error. So, oh, also one more important thing. Whenever you're justifying this on the AP exam, you are never going to set the error equal to the inequality. All right, so it's always going to be an inequality, and you always want to make sure that you want to prove that it's definitely 3 over 1,000. Now, this will always be the last FRQ, so this will always be inactive, meaning that you want to make sure that you aren't giving me anything silly and that you know for a fact that it is less than 3 over 1,000. So here's what I mean. Remember how we are using the next neglected term, which is going to be term number 7 in this case. So the error is going to be term number 7, which is going to be 3 over 2 to the 7th, and then times 8. Now, here's the problem. Unfortunately, I do not know if this is definitely 3 over 1,000, right? So what you need to do is make sure that you know that for a fact that this is less than 3 over 1,000 by simplifying this. So 2 to the 7th and 2 to the 3rd is 2 to the 10th. Now 2 to the 10th, it's 1024. And then you know that because it's 1024, that's definitely less than 3 over 1,000. So at this point, you could just stop there, and this is enough work to earn you full credit. Of course, you just gotta say the thing that I said earlier for number 19, where it's an alternate series error because terms decrease in absolute value to 0.